All right, guys, home stretch. So this is part 4 of the May June 2020 paper 1-1, and yeah, let's just go. All right, so I think we're doing questions 31 through 40 today. Yeah, let's just get to it. Okay, so these are all multiple selects. So remember that always for every single paper 1, the last 10 questions are always double bubble for chemistry. So, well, multiple bubble. So, just make sure you check every single answer first before moving on. All right, well, let's just get started. So, as you guys can see, A is 1, 2, 3, B is 1, 2, C is 2 and 3, and D is just 1. So, obviously, it's not every single combination, so I guess that is easier a bit, but, still good to check. All right, let's just get started. The definitions of many chemical terms can be illustrated by chemical equations. Okay, so which terms can be illustrated by an equation that includes the formation of a positive ion? Okay, so when you're forming a positive ion, that just means you're forming something that has a positive charge. So, I guess that's pretty straightforward. So, first ionization energy, an example of this, here, let me just say an example of this would be, I don't know, let's say we have neon gas, right? Neon gas would be going to Ne plus gas plus an electron. So that would be our first ionization energy. So the definition of that is basically you are taking 1 mole of a gaseous compound. So that's what we have here, Ne gas. It could be anything though. So it could also be like Fe gas if you want. So it could be iron gas. And you're basically taking out an electron and you're forming a positive ion. And that is the definition of first ionization energy. And that does indeed form a positive ion, so that is correct. Heterolytic fission of a covalent bond. Okay, so this one, the most common one we'll see in organic chemistry typically is that of halogens. So let's take a look at the bromine one, for example. Heterolytic fission is when one of the molecules takes all of the electrons in the bond. So this will actually go to Br with 2 electrons and then a Br with no valence electrons. So, well, actually, this one has a full octet and this one just has 6 electrons. So if you were to actually draw them all out, this is what it would look like, kind of like that. And what this means is this actually has a negative charge and this actually has a positive charge because bromine normally has 7 electrons, but, well, 7 valence electrons, and this one on the left has 8 and the one on the right has 6. So it's negative and positive respectively. And since this actually has a positive charge, you are actually forming a positive ion. So that is actually correct as well. But this last one, though, it seems like this one's a bit wrong. Enthalpy change of atomization, all this is saying is you're basically, this is the step you do for if you have like a solid or a liquid. For instance, if we were to bring that example of iron, right? If we wanted to get Fe gas, well, iron is solid in its elemental state. So what you're doing is the enthalpy change of atomization is making 1 mole of a compound into its gaseous form. And that is the definition of enthalpy change of atomization. As you guys can see, there's no ions being formed here. You're just changing the state to the gaseous phase. So that actually won't do anything. So in this case, only 1 and 2 is correct. Well, are correct. And that means that this will be answer choice B. And I believe that is the correct answer. Moving on, question 32. Which molecules have no overall dipole moment? Okay, so that just means we need a symmetric molecule or just a molecule that just, doesn't form polar charges. So boron trifluoride. If you guys don't know, boron is one of those unique molecules that does not need to form a complete octet. In fact, boron trifluoride is the most common example that you'll see here. Boron with any 3 halogens is actually in its most stable phase. It'll actually form a planar molecule with all of these having 120-degree bond angles. So that'll actually all cancel out because of the symmetry, and you're going to get no charge. And that means boron trifluoride is indeed a neutral molecule, so it has no overall dipole moment. Moving on, we have methane. So that's boron trifluoride. Methane is a tetrahedral molecule, so if you were to draw that out in its 3D way, you have those 2 angles like that, you have an H here, and then you draw the dash structure, and you have an H right there. So this is tetrahedral, meaning all these angles have a 109.5 degree bond angle. And because of the symmetry of this, you can kind of think of it as kind of a trigonal, I guess, a triangular pyramid, I guess. So if you were to draw it out, you can imagine it to be something like that, a triangular pyramid. And what that means is this also is symmetric. So since the center of this atom, the carbon would be like right here. This is actually a symmetric molecule, therefore you don't have an overall dipole charge, so that is actually correct as well. Now our last one's a bit more confusing. phosphorus pentafluoride. So if you were to draw this one out, phosphorus, the pentafluoride, the ideal way to want to draw this is, first of all, draw the top and bottom ones as 180 degrees from each other. Draw this one, so you'll know that this angle is 90 degrees. And the other ones you'd want to draw like this. So with a wedge here, so like that, and then a dash here, like that. And what this is each of these angles is 120 degrees. So if you were to actually like draw it out just like on its form, you can kind of think of it as being like this, and then like that. So you actually have a triangle on this part. So this is actually a trigonal bipyramidal molecule. And what that means is it is also neutral because these fluorines on this triangular plane is going to cancel out, kind of like this boron trifluoride you got here. And meanwhile, these two are basically at 180 degrees to each other. And you guys know that, if you were to take something like carbon dioxide, which is also linear, linear molecules are also nonpolar. So overall, this has a nonpolar charge. So this is also indeed nonpolar. So overall, all three of these, boron trifluoride, methane, and phosphorus pentafluoride, have no overall dipole moment. And therefore, our answer is, I believe, A. So that is how you would look at that. Make sure you guys know your overall geometries for molecules. That's a really handy thing to know. Let's switch colors this time. Let's say we do green again. All right. Moving on, question 33. So it says carbon exists in several different forms, and two of these forms are Buckminster fullerene, okay, our good old buckyball, and graphene, okay. You should know graphene as well, and that is that is one of the chemicals that is involved in pencil lead, which is not really lead, but a combination of clay and graphene, or graphite, but Buckminster fullerene is a fullerene allotrope of carbon. Okay, hopefully you guys know what that means. That basically just means it forms here, Buckminster fullerene is C60, so it actually forms a carbon network in the form of a soccer ball or a football, if you guys are from an international country. In America, you call it a soccer ball. Elsewhere, it's a football. But point is, it actually makes a lattice structure in the shape of I'm American, so a soccer ball. So that's that. And then the other allotropes that are fullerenes, you could have a bit larger shape. So it could be like an extended buckyball, I guess. So you could have like C80, I guess. But point is, there's a bunch of networks like that. So the specialties of both of these. So, wait, actually, let's look at graphene. Graphene is just a network of hexagons. Oh, well, that is not a hexagon. So it's just, at each of these ends is going to be a carbon atom. And you're basically just having a ton of these going out everywhere. So you basically just get one gigantic sheet of just carbon atoms, and that is what graphene is. And what ends up happening is each of these will actually form a bond to a lower sheet, and you'll basically have the same thing down below. And you're basically just having layered sheets like that, which is why if you rub pencil lead, the pencil lead actually just shaves off. That's how we use pencils to write. That's because the graphene is really easy to break on that plane. So actually, let me undo that. It's really easy to cut these bonds like this. So while these sheets are very strong, these bonds right here are really weak. So you can actually shave them off at that side, and it'll rub off, which is how pencil lead works. So moving on. Which statements about Buckminster fullerene and graphene are correct? Okay, so both do have delocalized electrons. So why this is the case? Each of these carbons, right, if you take a look at them, they're going to be bonded to other carbons like this, but they're actually going to have partial double bond character. And what that means is, due to resonance, each of these double bonds can actually transfer between any of these like that. So that's why I say it's partially double bond. So each of these are actually sp2 hybridized. And what that means is, since these electrons can just flow freely between these three bonds, that just means that these are all delocalized electrons. And that's also why, if you look at the buckyball, it actually transfers electricity throughout the outer shape. So if you have the buckyball, I don't know, let's say that's what it looks like, right? It'll actually transfer electrons throughout this outer shell, and it won't actually convey anything here, but it will transfer electrons around that outer shell. And electrons will also flow along the sheet for graphene. So they both have delocalized electrons, which is what actually allows that to be possible. They are both semi-decent conductors of electricity. So Buckminster Fullerene has a giant molecular structure. That is incorrect because, again, it forms a network of covalent bonds, so it can't really be a giant molecular structure. The carbon atoms in graphene form a tetrahedral lattice. We also just showed with this picture that that is indeed not the case. It's not tetrahedral. It's really more like, how would you say it, a honeycomb structure from bees, but at the same time just laid out in a really, really big sheet. So for this one, the only correct answer is actually number 1, and that means D is our answer for this question. So hopefully that makes sense. Yeah, the carbon allotropes are a bit strange. So yeah. Oh yeah, I guess they didn't say this, but graphene is also a allotrope of carbon because, there's only carbons involved. All right, moving on. Question 34. Let's swap colors back to red. Okay, so carbon monoxide burns readily in oxygen to form carbon dioxide. Okay, so carbon monoxide burns readily in oxygen to form CO2. Okay, what does this information suggest? Okay, so the first thing I'd start with is just listening at the equation. So you have carbon monoxide plus O2 gives you CO2. So if you were to balance this equation, you can either put a 1/2 here, which is typically standard, or you can do what I like to do and just multiply by everything by 2 to make sure there's no fractions. But either one's fine as long as you get the stoichiometry, right? What does this information suggest? Okay, let's see. So another thing you should look at is oxidation states. Oxygen is always -2, except for its elemental state, in which it's 0. So for that to be a neutral molecule, for here, carbon needs to have a +4 charge, and for here, carbon has to have a +2 charge. So what does that suggest? The +4 oxidation state of carbon is more stable than the +2 state. Well, since carbon monoxide burns readily in oxygen, all you have to know is that since that is the case, it is actually going to be a more stable molecule. So indeed, this is correct. So because this higher oxidation state is preferred since it burns readily, that keyword there is readily, this is actually a favored reaction, therefore +4 carbon, carbon with a +4 charge is much more stable than the +2 state. And moving on, let's see, the standard enthalpy change of formation of CO2 is much more negative than the standard enthalpy change of formation. Okay, this is actually also true because a more negative enthalpy change of formation is basically stating that the molecule is more stable. So if you have that in the case, basically what this is saying is CO2, since it has a more negative one, it is more stable than carbon monoxide, than CO. And we found from answer choice 1 that that is indeed correct, so answer choice 2 is correct as well. And our last one here, the value of the equilibrium constant, okay, so that is K. For the reaction, this is likely to be high. Okay, so first of all, they don't really say what K we should use. I'm just going to use Kp since everything's in gaseous form. So how you do this is first take a look at the reactants. So in this case, it's 2CO2. So P, CO2, coefficient of that is 2, so you'd have to raise it to the second power, so like that. Divided by, let's see, you have CO, so it'd be PCO squared, and then you have O2, so PO2, like that. So if you were to look at that, the reaction is favored towards the products, since we know that it burns readily in oxygen, and if it's favored towards the products, that means that the Kp value must be very high. So it must be very, very high, because if it burns readily, that means it's going to the products. If it didn't burn readily, then it would be leaning towards the reactants, in which case Kp would be very, very low. But that's not the case, so since Kp is high, well, yeah, it's likely to be high, so that is the correct answer. So in this case, all three are correct, so that is answer choice A, like right there. All right, so answer choice A. Moving on. The catalytic converters fitted to cars remove pollutants from the exhaust gases. Okay, we know that. So exhaust gases, and we need to know the catalytic converters. Some of the reactions that occur involve oxygen, which comes from air. Okay, so the most common one that you'll see, and you guys know this from paper 4, is the nitrogen monoxide plus carbon monoxide goes to carbon dioxide plus 1/2 nitrogen gas, like that. But in this case, we actually don't know. We don't need this reaction because we're looking for the pollutants that react with oxygen. So you're actually going to need to know 3 other equations to know how to solve this question, and you guys might not know it, so hope you follow along with this. So if you have any multiple of NO, so NOx, that could be NO, NO2, NO3, NO4, so on, you'll actually split that up into NX plus OX. So it actually splits up into different molecules like that. So most commonly you have like NO2. So that'll be, in that case, it would be NO2, well, NO2 would decompose to N2, 1/2 N2 plus O2, like that. But that's just an example. Point is, nitrogen X oxide will split up into NX plus OX. So that is one you need to know, but again, that doesn't react with oxygen, so you don't really need to know that. But in the same case, that also means that NO2 probably won't react with anything. But let me just show you the other two before I move on. The other one you need to know is the one that we actually did before. It's actually this equation right here. Carbon monoxide, or more accurately, 2 carbon monoxide, added to just regular oxygen, will actually become 2 carbon dioxide. So this is actually going to be one of the reactions, and as you guys can see, that is the reaction shown in number 3. So in option 3, that is indeed going to be one of our reactions, and the other reaction that we're going to need to know is the one with the fuel. So this is actually going to be one of them as well. So when you have unburnt fuel, right, they are multiples of alkanes, so it's actually going to be a formula of H4x, like that. So that could be like methane, ethane, and so on, and you'll actually have multiple ones. And what you do is you react that with 2xO2. So as you guys know, this is basically just combustion, right? So alkanes will combust with oxygen, and it'll become XCO2 plus 2xH2O. And why is that important? Well, you guys really don't need to memorize this one. You guys actually know this one, you know? So like, for instance, if you have CH4, we already know that that turns into, plus XO2. We already know that that'll turn into CO2 plus 2H2O. And then we just balance the oxygens like that, right? So this would actually be 2 right there. Yeah, it's basically just a typical combustion reaction, combusting an alkane. I'm sure you guys know that. So this unburnt fuel is actually just code word for alkanes. So just know that. So that will most definitely react with oxygen through a combustion reaction. So that is answer choice 2 right there. But as you guys can see, NO does not react with oxygen. It just kind of decomposes. So it undergoes its thermal decomposition and it forms a nitrogen gas and oxygen gas. So that is not our answer. So since only 2 and 3 are correct, that means answer choice C is the correct answer for this question. All right, moving on. Question 36. So chlorine reacts with sodium hydroxide in 2 different ways depending upon the temperature. Okay, so this one, let's see. Oh, well, if you ever get 2 reactions like that and you always spot this kind of compound, the first thing that comes to mind is a disproportionation reaction. And what that is disproportionation reactions are basically, it's a redox reaction. So it's a redox, but it's a redox reaction, which means, you know, oxidation and reduction occur at the same reaction, but it's by the same element. So in this case, sorry, this is just some vocab that you guys should know. So it's redox but by the same element. And what that means is, as you guys can see, chlorine gas has a neutral charge, but this chlorine has a -1 charge, as you guys can see. But since oxygen is always -2, this would have a +1 charge, so that you have that overall -1 charge. And same case for here, you have -2, so you have 3 of them, so that would be -6. Again, -1 charge, so this would be +5. So as you guys can see, chlorine possesses 2 separate charges. So you have -1 and a +1 for that one, and -1 and a +5 for this one. So those 2 different charges mean that this is a disproportionation reaction because chlorine, it undergoes both oxidation and reduction in the same reaction. So just a special kind of redox. And that also means this, since chlorine over here gets the higher charge, it's actually going to be the one with the higher temperature, because a higher temperature basically means that you have more energy, because energy is directly correlated to heat, as heat is, you know, a form of energy, thermal energy. So basically what that means is, since you're forming a higher charge, you're going to need more energy to form that higher oxidation state, and because of that, you need a higher temperature. So looking at the answer choices, reaction 2 requires a higher temperature. That is indeed correct. That is basically what I just said. The products of reaction 1 show chlorine in 2 different oxidation states. That is true. We see there's a -1 and a +1 state, so that is correct. The products of reaction 2 show oxygen in 2 different oxidation states. That is incorrect, because Hydrogen always has +1, well, except for certain cases, same case for O2. But in this case, oxygen is always -2, as you guys can see, -2 there, and in water it's -2 as well. So since it's always the same, this is actually not going to be right. So our answer choice is just 1 and 2, and that means that the answer to this question is answer choice B. Hopefully that made a bit of sense. And if you didn't know anything, hopefully that enlightened you a bit. Question 37. All right. We are on the home stretch. There's only like 4 questions left to go. All right. Moving on. Which of these reactions the organic compound oxidized by the given reagent? Okay, so looking at the reagents, we have HCN, so hydrogen cyanide, Tollens reagent, and Fehling's reagent, and we're given aldehydes. That CHO is the indicator for an aldehyde. So CH3CHO, that is basically going to be this. That is ethanol. That is what that is, ethanol. And if you react it with HCN, what ends up happening is it forms a mechanism. So if you guys don't know, it'll go by a mechanism reaction, and it'll actually form this. So you have H and the other one here, but that double bond O will actually turn into an OH, and you're actually going to get a cyanide attached to it like that. So hopefully you guys remember this. This is the hydroxynitrile. The hydroxynitrile. Yeah. So this would be what? 1, 2. So actually no, it would be 1. It would be 1 hydroxynitrile. Well, no, 1 hydroxyethanitrile, like that. So that's what that is. So this is actually not going to be an oxidation reaction. It's really just a substitution reaction. So that's not going to be right. Meanwhile, since both of these are aldehydes, I'm not actually even going to draw them out. I'm just going to tell you what they do. Tollens reagent, if you guys don't remember, is a test, just like Fehling's reagent. These are both tests for aldehydes. They test for aldehydes and not ketones. Well, I can't spell. Not ketones. And both of these will give positive tests for aldehydes. Tollens reagent, so Tollens will give you a silver mirror. Oh my god, my handwriting. And Fehling's will give you a brick red precipitate. So both of these will actually give you a positive test, and both of them are oxidizing agents. They're weak oxidizing agents, however, but they still oxidize the aldehyde into a carboxylic acid and will give you a positive test. So option 2 will give you silver mirror, and option 3 will give you a brick red precipitate. Therefore, our answer here would be, let's see, well, I actually don't know. Answer is C, because it's 2 and 3. So that is answer choice C. All right, question 38. When the apparatus is set up as shown, an orange precipitate forms. Okay. And, we have 2,4-DNPH, or if you're going to be fancy like them, 2,4-dinitrophenylhydrazine. What this does is it tests for a CO, and it turns the solution and forms a orange precipitate if you have that carbonyl. So that just means aldehydes and ketones. It does not work for carboxylic acids because those guys are a bit special. Meanwhile, we have acidified potassium dichromate and a warmer. So this is not a reflux system, so you got to keep that in mind. What that means is it oxidizes alcohols as such. So it turns primary alcohols into aldehydes. Remember, this isn't reflux, so it won't go into a carboxylic acid. That only works if you keep going. But as you guys can see, at the moment it turns into a gas, it just leaves. So that's not going to be the case. So primary alcohols will go to aldehydes, secondary alcohols will go to ketones, and tertiary alcohols will do nothing. There won't be a reaction because they are too stable. So what could compound Q be? All right, so that just means that we need to make sure that it's going to be a primary or secondary alcohol that goes. That way we actually get a successful test and get a carbonyl. Let's move on and just solve it, I guess. CH3, CH2, CH2, OH. So that's this, I believe. And that will oxidize to an aldehyde because that is a primary alcohol right there. So that goes like, let's see, it'll be like, actually, let me redraw that. It'll go like this, OH, like that. And again, it's not a carboxylic acid because it's not under reflux. So that will give a positive test. So that is a correct option. So option 1 would be working. Option 2 is CH3, CHOH, CH3. And if you were to oxidize that, that is a secondary alcohol, as you guys can see. And that means that that will become a ketone when reacting with acidified potassium dichromate, 7. So that is a ketone. That is indeed a carbonyl, so that will work. This last one, though, this one, is going to look like this. And what that is that is a tertiary alcohol, because as you guys can see, there is 1, 2, 3 carbon groups. So that is tertiary, and that means this is going to have no reaction. And no reaction means there's not going to be no CO, COO, so there's no carbonyl group. Therefore, that will give you a negative test, and you just won't get anything with the 2,4-D and pH. So, since it's only option choices 1 and 2, this question, the answer is B. All right, moving on. With only 2 questions left, and then we're done with this entire question booklet. Wow. Question 39. Chlorofluoroalkanes that diffuse into the stratosphere are broken down by ultraviolet radiation. Okay, so this is a chlorofluorocarbon question. So CFCs, if you guys don't know, those were banned in, I believe, the 1990s, I think, because they generate chlorine radicals. So again, this is kind of a trivia question. So I actually know the answer to this one right away. There's no fluorine radicals and there's no alkyl radicals. It's just chlorine. So let's see, the answer for this one will be option D, and I'll explain this for a second. All right, so chlorofluorocarbons, if you guys don't know, they form chlorine radicals, and how they work is this. So you have the center carbon, right? You have a chlorine, a fluorine, you have a hydrogen, and then it can actually be other stuff, so I'm going to call R. So what happens here is UV light will actually cut this bond right here, and it'll make a chlorine radical, which is a chlorine with an electron like that. So what ends up happening is this will actually react with ozone, and it'll form oxygen and chlorous oxide, I think, hypochlorous, I don't know, CLO, I don't know how to name that, I guess, CLO, and how this works is, here, let me just show you the reaction, how that works. So if you guys don't know, ozone looks like this. So what chlorine will do is chlorine will actually form a reaction with this oxygen, cut that off, and it'll give you oxygen, which looks like this. Well, oxygen, which looks like this, and then the CLO. And what the CLO will do is it'll actually react with another CLO. So if you have a chlorine oxygen like that, and you have another one on another side like that, what this will actually do is each of these will actually react with each other, and it'll form this gigantic molecule that looks like this. And the reason why this becomes dangerous is because this is actually a propagation reaction. So what ends up happening is one of these chlorines will actually split off. So here's how it'll work. ClOOCl. One of these chlorines will split off like this, so it'll go homolytic fission, and you'll get a ClOO like this. Oh, whoa, sorry, yeah, that's right. And then you get that, and then you get a chlorine like this, and that is a chlorine radical. So this will actually continue and go back to this step right here and continue to wreak havoc and break down other ones. And you might ask, okay, well, that happens. Then what about the other one? Why does this continue on for so long if that's stuff that happens? Well, this one does that too. So this ClOO, what's that? Also splits into 2. So you end up getting this, well, you end up getting this oxygen like that, plus Cl radical. So you have 2 chlorine radicals like that. So these chlorine radicals will actually keep going until they react with each other. So when you have a chlorine radical plus a chlorine radical, these will become chlorine gas. But this happens only after about 1,000 molecules of ozone are broken down. So as you guys can tell, that means chlorine radicals can wreak havoc in the ozone layer, and that is why it is so dangerous. Also, by the way, this will actually convert into this, and that is why that is oxygen gas. Hopefully you guys understand that. So chlorine radicals are really scary, and that's also why we banned these in the 1990s because they are the main reason why there's a giant gaping hole in the Antarctic, like above the Antarctic. Yeah, that's basically because a bunch of the chlorofluoralkanes grouped up there and just blew a hole in the ozone layer because they reacted with the ozone, turning it into oxygen, meaning UV light can just break through. So just make sure you know that only the chlorine one splits off, the fluorine and the carbon actually just stay. And the reason for that is because chlorine is partially reactive. Fluorine basically never reacts with anything unless it's hydrofluoric acid, and the carbon really doesn't like to form a radical because carbon's a pretty neutral molecule. So yeah, answer choice D. Question 40. Ooh, last one. Okay, so a mixture of the three isomers of C2H2Cl2 is polymerized. Okay, well, let's end this one with pink, let's say. All right, so of that. So the three possible ones you actually can get are here. Your first option is if, okay, so first of all, you know that from the answer choices, this is going to be addition polymerization. So you should start out by drawing that double bond. And the three possibilities are, you have both the hydrogens on top, so like this. You can have, okay, so this would be the cis isomer. So you can also have the trans isomer, which is going to be basically the chlorines are on opposite sides, like this. Or you can have the isomer where there's going to be no cis-trans isomerism, which is just basically both of the chlorines lie on one side, like that, and both of the hydrogens lie on one side, like that. So what this means, oh my god, wait, let me redraw that a bit better. What this means is when you're forming the polymer chains, you're actually going to get variations. So you might wonder, well, none of these actually really show anything, so the only one I really see that matches is this one, because it's this one. So you might say that question 2, well, option choice 2 is the only correct one, and you look at it and you're like, oh wait, only option 2 is not an option. What am I doing wrong? Well, keep in mind, these polymer chains actually work for a long chain. That's why a polymer chain is called that, because you can actually have up to like 1,000 of these, and maybe even more. And that's why we have such big plastic products. They're basically just polymers. So if you take an example of that, this is actually going to be a combination of this one right here and this one right here. So it's going to be 3 plus 1. And I'll explain why that is by drawing them out. So if we were to just split them up, right? Let's just draw the isomer. So this one here, when you're polymerizing it, it looks like this. So here, wait, C, C. So you have Cl, Cl, and you have H and H. And as you guys know, polymers will stretch out. And if you add the 1, which is this one right here, you have CC, and then you guys know there's the H, Cl, Cl, H, like that. And they'll continue, but let's just take a look at this. If you guys look, if you take just this middle portion right here, notice how it matches up exactly with the one we have there. You have the chlorine here, hydrogen here, and chlorine here. So that one is how that works. So hopefully you guys get the pattern now. And that's how you basically just keep going and solving it. As you guys already know, I showed you the second one is correct because it's literally just the first one. It's when you polymerize it, it just goes like that. You have hydrogen, hydrogen, chlorine, chlorine. So this one just is what it is. It's just like that. Boom. Option choice 2 is indeed correct. Option choice 3 now is actually going to be a combination of 2 and 3, because what it is you have the carbon, you have hydrogen, chlorine, chlorine, hydrogen. Obviously they extend, and then drawing them out again, Cl, Cl, H, like that. If you were to look at this middle portion again, notice how the chlorine matches up with the chlorine, and then there's 3 hydrogens where there are 3 hydrogens. So this one is correct as well. So that means all 3 are correct, meaning answer choice A is the correct answer for this question. And that actually concludes this video and this series, actually. So for this paper 1, well, not the series, just this 4-part series, I guess. This 4-part series now concludes. That was all 40 questions. Hopefully, guys, you learned something new, and hopefully it did indeed help you guys. I'll be back with another paper 1, probably maybe later or sometime tomorrow. And yeah, that's basically all I had for you guys today. Hopefully you guys enjoyed. Um, Hopefully you did learn something new and be proud. You have just finished a paper one. And yeah, so I guess happy studying. I'll see you guys next time. Bye.